All right, for today, we're going to be talking about IceCube. IceCube is a neutrino experiment that is buried deep down within the ice of the southern polar cap. So let me pull up a cool image of IceCube neutrinos. See if we can get a good image of it that we can have in the background. Let's use this one in the background because it looks cool. Open image in new tab. There's the new tab. All right, so that is the, I guess, the science base camp for IceCube. We also should take a look at where IceCube is located in the world. So somewhere on the flat Earth is an ice wall, and in that ice wall is located a scientific base, and on that scientific base is IceCube. Now, for some reason, Google is not giving me a spherical planet. There we go. That's what we're talking about. Is that the international dateline? Okay, so around here, where is IceCube located? So let's go directly to the website itself. So the main investigator on IceCube is at the University of Wisconsin. They're kind of the main group. Let's see if they have a location. IceCube overview. So IceCube means it's a cubic kilometer, and they're using ice as their, we've seen neutrino detectors before where you use water as your mass, like your detector mass, and then the neutrinos come in, hit the particles in the water, produce Cherenkov radiation. So they produce electrons that are moving fast, and then that gives us a Cherenkov radiation, and then you have a bunch of detectors lining it. So we've seen that with the Super Kamiokande experiment, where you have a detector volume filled with water, and then you have the photomultiplier tubes surrounding it. So when the Cherenkov radiation, like neutrino comes in, produces Cherenkov radiation that gets detected by the photomultiplier tubes around here. IceCube is a bit different. Now they're using solid water, and the detectors are strung. We'll see what the detectors look like, but they're basically on strings that are hanging down into the ice. And it's a square kilometer surface area and about a kilometer deep. And so there you go. There is IceCube. The location, where is it located? It's on the near the South Pole. I don't know that it's actually at the South Pole. Deep in the South Pole, encompassing a cubic kilometer of ice, IceCube searches for nearly massless subatomic particles called neutrinos, which we've already talked about, the high energy astronomical messengers of information, etc., and so forth. It doesn't say here where it's located. Maybe it will say quick facts. Let's try quick facts and see where it's located. If we need to, we'll have to go over to Wikipedia. A bunch of stuff happens. It's a cubic kilometer. It's at some depth. 7 years to complete the construction. And that ice at the South Pole. Why don't they just say where it's located? All right, here we go. IceCube neutrino. Just because I want to know where it's located. How does this compare to other neutrinos? This is way bigger than any other neutrino detector that's out there. Let's see. With one exception. There is an exception to that. Okay, it's at the Amundsen-Scott South Pole Station. Amundsen-Scott South Pole Station is the United States scientific research station at the South Pole of the Earth. This is not on Mars or on the Moon. It is the southernmost point under the jurisdiction, but not sovereignty of the United States, because the treaty says that no one is sovereign over that, but we get to jurisdiction over it. Here is a map of Antarctica, and the Amundsen-Scott Research Station is apparently right at the South Pole. So there you go, right at the South Pole. And there are these other research stations that are kind of all around here. Vostok. What are some other ones that we've heard about? Dome. There's like Dome C. I'm not sure where Dome C is located, but there's other things that are located there. I think the South Pole Telescope is on Dome C. So these are the different stations, and Amundsen-Scott Research Station is right at the bottom. Okay, now how this compares to other neutrino detectors, a cubic kilometer is big, right? There's no other neutrino detectors that are that size, except for one called ANITA. This will be a subject of a future stream. ANITA, neutrino detector. This one, Antarctic Impulsive Transient Antenna, it's a balloon-borne experiment. So this is the detector of ANITA, and it's suspended from a balloon. And what it uses, it looks also for signatures of neutrinos, but these are signatures of neutrinos where you're using the entire continental ice shelf of Antarctica. So you'll get the production of whatever the particle is that you're looking for through the ice, and all these detectors are pointed slightly downwards, so it's suspended by a balloon, and then all the detectors are pointed slightly downwards towards the ice, so that the particles coming up through the ice, or the signature that you get from them, whether it's radiation or whatever, comes up and hits this. And so they're using not a cubic kilometer, but like thousands of cubic kilometers of ice as their detector volume. So I think that would be probably the largest neutrino detector in terms of what the detector mass is. So that is ANITA, but that's something for a different day. I will say that for ANITA, the Antarctic gear that they wore on The Big Bang Theory. So when Sheldon et al. Went down to Antarctica to look for magnetic monopoles, and they were wearing like red gear to stay warm. That's Arctic gear that was used by the ANITA experiment, because the guy that's on ANITA is a consultant on The Big Bang Theory. Okay, so back to IceCube. It's a cubic kilometer. We'll take a look at what the detector looks like right here. Oh, so that's the observatory. I mean right here. I mean, not right there. So let me pull up a different image. IceCube, neutrinos, and let's pull up directly from Wikipedia, because it will aggregate the images better. Wikipedia. So this is what the detector looks like. There was an earlier detector that was built kind of in the same vein in the 90s. That one's Amanda. So you can see Amanda right here. And then you have this deep core. So deep core is another subcomponent of the detector. So here's what they have. The South Pole this actual station is slightly off to the side. And then they have the IceCube laboratory, which was what we saw, that building that's kind of suspended above the surface. And then they have 80 stations, 80 stations, which are these locations here, with another set of optical detectors. So 2 ice-top Cherenkov detector tanks. So that's looking, ice-top is stuff that's on the surface of the Earth, and that's looking for Cherenkov radiation coming from the atmosphere, so particles produced in the atmosphere. When I do the Pierre Auger Cosmic Ray Observatory, we'll see some more of those kinds of detectors. 2 optical sensors per tank, 320, so that's for ice-top. 320 optical sensors. And then in this thing, so ice-top is the stuff at the surface. These strings, I think, how many strings are there? 86 strings. I thought there were 89, but apparently there's 86, or at least at this moment there were 86 strings, including the 6 deep core strings, 60 optical sensors on each string. So what they did is they drilled down into the ice. They had to go down through the snow first. So the snow is different than the ice. The snow hasn't compactified. The surface of the snow hasn't compactified enough to be ice. And so they use a drill to go down through the snow portion of the surface of Antarctica. So let me draw a picture of this. So here is the surface of Antarctica. It looks like this. And this is snow, and then there's ice underneath it. And then here's your station. They have a drill. The drill goes down through the snow. It's about 50 meters deep until they hit the ice, and then they pull the drill back out, and then they run a hose down into the ice, and they bore the rest of the hole a long way down, like 2 kilometers down, using basically hot water. So they run a hose of hot water down into the ice. So now you have this big column of hot water that is 2 kilometers long, roughly. we'll look at detail at the depth. Oh, I guess it has the depth right here. So it's almost 3 kilometers at the base. 3 kilometers down is the bedrock. So this is 2.5 kilometers down. So they have this hose running down 2.5 kilometers of hose. That's pretty gnarly. And then they lower these strands of optical sensors. Eiffel Tower's right here, which is kind of wimpy compared to the size of this whole thing. Each of these strands that they lower down has a set of optical sensors on them. So let's see if we can find what these optical sensors look like. I had them on display. It's IceCube optical sensors. It took them about a decade to build it. They could do, when they actually started drilling, drilling in this hot water drilling type thing, they were able to do apparently 1 strand every 2 days. But it took them more than 1 season to put it together. And then you have to build all the infrastructure around it and stuff like that. So you have to build the building that you're going to do your analysis from and so forth. Was it like 6 years that it took to build, or 5 years? Let's see what it says. Construction began in 2005. The first string was deployed and sufficient data was collected to verify that the optical sensors were functioning correctly. And then here is the strings installed, 86 total strings. So 5 years to build, and it's been running for a decade. This is what the detectors look like on the strands. So it has the cabling. These are the steel cables that suspend. So you have this long string of detectors on it. Let's see how many detectors are on each individual strand. So Amanda, okay, I talked about this already. Where does it look like? Here, Amanda, this smaller thing, that was a proof of concept. Let's do a smaller one. It's less expensive, just to show that we can get the signal down into the ice and back, from the ice up to us. It shows that we can deploy these strands the way that we think that we can. You can do some science with it, but the goal is a technical demonstration. Before you do a cubic kilometer, you want to do, 100 cubic meters or something like that. So Amanda was built in part, it served as a proof of concept for IceCube, and it was turned off in May 2009. The IceTop array is a series of Cherenkov detectors on the surface of the glacier with 2 detectors approximately above each IceCube string. IceTop is used as a cosmic ray shower detector, and we will do some other things about cosmic ray detectors. The deep core. So the deep core is this portion of the detector array where they added more strands to have a higher concentration of detectors in that area. So they have all these detectors spread out. They wanted to have at least a region where there were more detectors, and so they lowered a few strands. You can see the footprint up here, the deep core footprint. So it's way down under the ice, and you have a larger density of detectors down here. So the issue that you confront with these kinds of detectors is IceCube is designed to look for the highest energy neutrinos. The highest energy neutrinos, what they will do is they will come in, and just like with the other neutrino detectors, the neutrino comes in, here's the ice, here is your strands of detectors down here. It comes in, it hits an electron. The electron accelerates at very high speeds, or is accelerated to very high speeds, and emits, because the electron moving through ice is traveling, the speed of the electrons is bigger than, this is an E, bigger than 0.75 C, like 75% the speed of light. In ice, light travels at 75% of the speed of light in vacuum. And so once the electrons are traveling faster than the speed of light in the ice, then they will emit Cherenkov radiation. And so you get Cherenkov radiation, and all of these detectors will pick up that Cherenkov radiation, and then you can use that information to infer the energy of the neutrino that came in, this neutrino here that came in and produced that high-moving, fast-moving electron. So the challenge you face is that the really high energy stuff is rare. And so if you want to detect them, you need to have a large detector volume. You might get one of these neutrinos per month per cubic kilometer. And so if you want to detect any in, say you want to have a year you might only get 10 detections in a year, or something like that. That's what you would get if it was a 1 per month per cubic kilometer. You would have 12 detections in a year. So I think they do a little bit better than that, but that's the point, that the very high energy stuff is rare. If you look at the spectrum of neutrinos, the number of neutrinos that you get at a given energy, it would be some kind of graph like this. So the number that you get as a function of energy of the neutrino, it falls off very steeply. And so if you're only looking for these things, you have to have a large detector volume in order to find them. What that does, though, is it makes you less sensitive to lower energy stuff, because the lower energy stuff is going to have a smaller, it's going to produce a signal in a smaller volume. You'll get more of them, but it's not going to be able to produce as much radiation, as much of the Cherenkov radiation, and as a consequence, it's harder to detect. And so having this deep core allows them to find lower energy neutrinos. So that's what this deep core string is. So 360 additional optical sensors. PIGNU, Precision IceCube Next Generation Upgrade, is a proposed extension that will allow detection of low energy neutrinos, GeV energy scale, where the deep core is 100 GeV, and the actual IceCube itself is for like TeV, PeV, 1,000 or 1,000,000 times higher energy than these ones. So the deep core is looking for things that are 1,000,000 times less energetic than the really high energy stuff. Let's see. Oh, this is interesting. There are no deep core DOMs, that's whatever these is, digital optical modules, between 1850 meters and 2100 meters, as the ice is not clear in those layers. So the ice is transparent at these different, at different depths, but there are some layers in the ice where you might have contamination from, Antarctica was in some location, or maybe there was a big volcanic eruption or a series of volcanic eruptions that deposited a bunch of soot on the ice, or maybe the temperature pressure conditions are such that the ice isn't transparent. But for the most part, the ice is really transparent, but they mapped out, they take a core, map out, at this depth we're going to run into these problems, and so that's why they choose the detector strand the way that it's built, or why they space out the detectors when they're built. IceCube drilling tower and hose reel in December 2009. So here's the hose reel. That's 2 kilometers worth of hose, and then here's the tower situated above the hole that they're currently working on. Then they're going to move the tower to the next hole as they flush it with water in order to drop these strands down. 28 neutrino in November 3rd. So we'll go into some of the science results that they have, but this was, I think, IceCube was the first detector to find neutrinos that they knew came from extragalactic sources. So not within the solar system, not from the sun, not from supernova, and not from nearby galaxies, but like distant galaxies sending stuff up. 60 modules, DOMs are deployed on strings of 60 modules. So there's 60 of them, basically a kilometer down. So they're several hundred meters across, or separated by several hundred meters, it looks like. "60 optical sensors on each string, and they're a kilometer long." So that is the structure of the IceCube observatory. Let's see, anything else? We talked about Cherenkov radiation already. It can detect other types of particles. Here we go. Realistically, an experimenter would need more space than just one DOM to the next to distinguish 2 cascades. So double bang searches are centered at PeV energy scales. What is this? Tau leptons can create cascade events, but are short-lived and cannot travel very far before decaying, and thus are usually indistinguishable from electron cascades. All right, what is this talking about? Is this cosmic ray stuff? Let's see. IceCube is more sensitive to muons than other charged leptons because they are the most penetrating and thus have the longest tracks in the detector. So these are things that are produced. So this type of detection with the muons will typically be of a form that looks like this. So here is your ice layer with your detector down here. You have the atmosphere up like this. You have a cosmic ray come in. Cosmic rays are always happy. So the cosmic ray comes in and creates a shower of particles. So here's the shower of particles, including muons. And it makes basically everything. The higher the energy, the more particles it can produce, but it produces a bunch of muons. Muons themselves decay in a few microseconds, but if they're moving with high enough energy, then the time dilation, the relativistic effects, makes it so that they are able to survive far enough down here in order to produce a shower of particles in the detector down here. It's more sensitive to muon than other charged leptons because they are the most penetrating and thus have the longest tracks in the detector. Thus, if the neutrino flavors so here's what's going on with the muons. Why they have the longest tracks. Electrons interact with matter. And so, there's a bunch of electrons already around, and the ice is made out of electrons to some extent, right? That's a large fraction of the constituent particles. And so electrons are going to interact with a lot of stuff. Muons, on the other hand, it's a different form of matter. And so it's going to have fewer couplings. It's going to be able to penetrate through the ice deeper. Tau leptons, so these are basically like super duper heavy electrons, they don't live very long. They live much, much shorter lifetimes than muons do. And so they leave only short tracks. Let's see, it's more sensitive to muons than other charged leptons. Thus, of the neutrino flavors, IceCube is most sensitive to muon neutrinos. An electron resulting from an electron neutrino is typically scattered several times before losing enough energy to fall below the Cherenkov threshold. This means that an electron neutrino events cannot typically be used to point back to sources. So that's interesting. So electrons will come in, they'll scatter a bunch of times, and so you get a Cherenkov cone. So electrons will come in, they'll bounce around. That's not bouncing around quite the way that I wanted to. Electron will come in, the neutrinos will bounce around, and so when you get a detector, it will be coming from a particular direction, but because it's scattered, you can't, the direction that you would trace back does not match the incident direction. So with muon neutrinos, they tend to come in a straight line, they don't bounce around, they produce a Cherenkov cone, and then you can run this backwards and point it back towards the original source. That's what it's talking about there. But they are more likely to be fully contained in the detector, and thus they can be useful for energy studies. So you can use electron neutrinos to study the energy because all of the light is trapped within the detector, even though the direction that the original electron came from is not available. These events are more spherical or cascade-like than track-like. Track-like meaning that they leave a trail of detector firings through the system. And we'll take a look at what these detector firings look like. Leptons can also create cascade events. Tau leptons can also create cascade events. So these are super duper heavy electrons. You have electrons, you have muons, which are heavy electrons, and then you have taus, which are super duper heavy electrons. But are short-lived and cannot travel very far before decaying, and they're thus usually indistinguishable from electron cascades. A tau could be distinguished from an electron with a double bang event where a cascade is seen both at the tau creation and decay. It's only possible for very high energy taus. Hypothetically, to resolve a tau track, the tau would need to travel at least from one DOM. So that's one of those. And those DOMs, the optical detectors, they're about the size of a bowling ball. Traveling near the speed of light would require 20 TeV of energy for every meter traveled. An experimental would need more space than just one DOM to the next to distinguish between two cascades. So you need to have one event where a bunch of detectors fire, and then you have to have a second event at the decay of the tau where also another bunch of detectors fire, and you have to be able to distinguish between those two bursts of particles. And so it takes super high energy to be able to produce the tau, have a bunch of particles come off, and then the tau itself decay and also have a bunch of particles come off. It takes a lot of energy to do that, and there are only a small number of particles that are moving fast enough to do that. So how do they know that these things, so we'll take a look at some of the results. How do they know that they're not from the solar system? It's because with a muon track, you can see when the detectors fire. The timing precision with these detectors, so they have these photon detectors down there, they can measure the timing precision, the arrival time of the photons to like 2 nanoseconds. 2 nanoseconds is 2 feet. Light travels at basically 1 foot per nanosecond. So 2 nanoseconds is 2 feet of light travel distance. And so when they have the detectors firing, they can reconstruct when did the photons arrive at all these different locations, and then run the thing backwards and say where did it arrive from. And with muons, because they come in straight, instead of bouncing around a lot, you get a good directionality in your data analysis. Let's see. Searches are underway but have not so far isolated a double bang event. There is a large background of muons created not by neutrinos but from astrophysical sources okay, not by neutrinos, but by cosmic rays. So those are the ones in the atmosphere that I talked about. Impacting the atmosphere above the detector, there are about 10 to the 6 more, a million more cosmic ray muons than neutrino-induced muons observed in IceCube. Most of these can be rejected using the fact that they travel downwards. So you would have the firing of the detectors in a vertical line instead of in a horizontal trajectory. Most of these things can be rejected by the fact they're traveling downwards. I said that already. Most of the remaining upgoing events are from neutrinos, but most of these neutrinos are from cosmic rays hitting the far side of the Earth. So you produce a bunch of cosmic rays at the far side of the Earth. The muons will decay and produce the muon neutrinos. The Earth really doesn't get in the way of them for the most part. Like most of them make it all the way through the Earth, and then a tiny fraction of them will appear in the detector. So you can get atmospheric stuff coming through IceCube either from directly above it or from the opposite side, from the North Pole, basically, with the neutrinos traveling through the Earth. And so that would look like, so you have the atmospheric neutrinos produced up here from cosmic rays. You also would have atmospheric neutrinos produced at the North Pole from cosmic rays, where the particles themselves decay into the neutrinos, which then propagate upwards. And so you can reject these ones, even if some of them are from the really high energy neutrinos coming from space, instead of neutrinos that are produced in the atmosphere. You would just reject them all because it's only 1 in a million that are the ones that you're looking for, at least for that kind of thing. Let's see, the experiments in the past few decades got really complicated. It's no longer as simple as observing an interferometer or putting an atomic clock on a plane or observing how much light. So different experiments, as you need more precision, or if you're looking for more extreme events, then the experiments tend to scale up. So there's definitely truth to that. All right, let's see. Experimental goals. So let's take a look at what they have as their research highlights. So they can do neutrino astronomy and multi-messenger astrophysics. So multi-messenger astrophysics is the study of, you have some event like in-spiraling black holes. You have a black hole merger. You're going to get gravitational radiation coming from that. You're going to get cosmic rays that come from that, although cosmic rays are a little bit of a different animal. We'll talk about that in a moment. You'll get high energy gamma rays coming from them. You'll get low energy stuff, radio wave type things. And so you look at what do we see coming from the gravity wave observatories? What do we see from the high energy gamma ray observatories? What do we see from the optical observatories? That's multi-messenger. What do we see in neutrinos? Do we see a burst of neutrinos coming from a particular direction? And then because they all arrive simultaneously, so this multi-messenger astrophysics is only possible because we can do time-resolved observations for a variety of different types of particles coming off of these different things. So you have an explosion, it throws out a variety of different kinds of particles and light at a variety of different wavelengths, and all of those things arrive, and you can time the arrival to know that they all came from the same object, and then you can get more information about what that object was and what it went through right before its demise. Let's see. So it shows here, this is actually something that I found this to be a very interesting image. So this is showing like why we built the, and I say we, I mean the scientists, built IceCube. If you look at different kinds of particles that can come through us, cosmic rays here, neutrinos, gamma rays, X-rays, so this is the energy of the sources, or the energy of the particles. So really high energy cosmic rays, neutrinos come from really high energies, gamma rays, X-rays, optical and infrared, that's all these different kinds of energies in terms of electron volts. Visible light is 1 electron volt, right? So that's optical and near infrared, or optical and infrared is right here at essentially 1 electron volt. And the issue is that the universe is opaque to photons. So radio, optical, X-ray, and that kind of stuff. The universe is opaque to these things at really high energies. For example, if you have really high energy gamma rays, so TeV gamma rays, TeV is what, 10 to the 12? GeV is 10 to the 9, TeV is 10 to the 12. So TeV gamma rays that are have the energy of the W and the Z particle, cannot travel through the universe more than 100 megaparsecs. So this is distance in megaparsecs. So this basically says how far can particles or objects with these energies travel, starting at 10 to the minus 3 megaparsec. So that's basically from the galactic center to us, because we're about a kiloparsec. So from the galactic center to us, we can see basically everything. If something goes off in the galactic center, we'll be able to see it all. But as you go to larger and larger distances, so the nearest galaxy, that would be the Andromeda Galaxy, notice that neutrinos of certain energies, photons of certain energies cannot make it from the Andromeda Galaxy to us, right? So you have something that's whatever's, I guess it's a PeV, a peta electron volt photon coming from the Andromeda Galaxy would be stopped by its interactions with probably the cosmic microwave background radiation in this case. I don't know that for sure, but that's what we're going to go with. That you have the cosmic microwave background radiation photons, and so you have really high energy photons coming from a nearby galaxy like the Andromeda Galaxy, and it would interact with the CMB photons and probably produce some kind of particle. Then you lose all the information that it came from. I know for a fact that that's what's going on here with these blazars. So blazars can often emit gamma rays of tera electron volts, that's 10 to the 12 electron volts. And notice that blazars, the nearest blazar is 100 and some odd megaparsecs away. So 100 megaparsecs away is the nearest blazar, and blazars can emit radiation that is at this energy, and the universe is opaque to that. It's opaque to photons. And the reason it's opaque to photons is because what you get is the following. You get, here is your blazar, okay, and this is the jet of stuff coming off of it. Of course, we want it to go this way, so let me redraw that so that it's actually oriented in the correct direction. Here's your blazar, so that's a galaxy, active galaxy. It's got a jet of stuff coming off of the center of it, so here's the disk, here's the jet of stuff coming off of that blazar, and then here's you looking at this blazar with your telescope saying, wow, that's amazing. And you want to study the blazar in all different wavelengths of light. You want to study it in the radio, you want to study it in the visible, you want to study it in the really high energy TeV gamma rays. The problem is that in between the blazar and you is a bunch of light. So this is an artist's rendition of photons. These photons are infrared. This is the cosmic infrared background, infrared light that's left over from star formation, that's just given off by stars in general. So there's a bunch of infrared light just out there in space that came from a variety of different sources. The problem is that the energy, the TeV gamma ray energy that's coming from here, so here's your photon, high energy photon coming in, it will interact with these cosmic infrared photons and produce what you get is, here's one photon, here's another photon. If you switch it to the center of mass frame, what you get is electron-positron pairs. Okay, the electron-positron pairs will reannihilate and produce another set of photons. However, these photons that are emitted here are no longer propagating in the same direction. They don't have the same information as this photon here that you're actually looking for. How you can tell that this is what's going on is that the infrared photons are going to be something on the order of 1 electron volt, maybe a bit less than that, like 0.1 electron volt, something like that. And these TeV gamma rays, that's 10 to the 12 electron volts. And so here's what you do. When you transform to the center of mass frame, it's the geometric mean between these two things. And so let's say that this infrared background is actually 10 to the minus 2 electron volts, because that will make it a little bit easier for me, because then I don't have to do the math on a calculator. I can do it in my head. So the geometric mean between these two things, you take the energy 1, energy 2, you multiply them together, you take the square root of that. This is a 2. And what do you get? Well, let's try it. So here is the energy of one is 10 to the 12 electron volts, and the energy of the other is going to be 10 to the minus 2 electron volts. Maybe I shouldn't have done it with 10 to the minus 2. Well, we're going to do it, and we're going to see what happens. Okay, I lied. We're going to do it with 1 electron volt. So that is, 1 electron volt is in the near infrared. Okay, this way my story will hang together and I don't have to be embarrassed later. I'll just be embarrassed now. Well, we won't be embarrassed later. And so 10 to the 12 and 10 to the 0 electron volts, because 10 to the 0 is 1. You multiply these things together, which means you add the exponents. That gives you the square root of 10 to the 12 electron volts squared. You take that square root and you get 10 to the 6 electron volts. Okay, and the mass of an electron is 500,000 electron volts. That is the mass of the electron. If you're going to pair produce things, then you're going to produce an electron and a positron pair, and they both have the same mass. So you have the mass of the positron. So that would be E plus. Mass of the E plus is another 500,000 electron volts. And so when you add these two numbers together, 500,000 plus 500,000 is 1 million electron volts. And so when you have these two, the TeV gamma rays coming in, and you have the cosmic infrared background, when they hit, they will collide with an energy. The center of mass energy is 1 million electron volts, and that gives you pair production. That's exactly the energy that you would want to have in order to readily produce electron-positron pairs. And once you produce the electron-positron pairs, then you lose the information that came before it. The photon is gone. Its information is now gone. And so that is why the universe is opaque to a lot of these high-energy photons. So here, this is the blazars that emit TeV gamma rays. The universe is opaque to those photons. This one, my suspicion is that this is from the cosmic microwave background. How could we tell this? So the infrared has a temperature of like 300 Kelvin. You go a factor of 2, factor of 100, I mean, 2 zeros, and that gets you to 3 Kelvin. 3 Kelvin is the temperature of the cosmic microwave background radiation. This was at 10 to the 12. This is at 10 to the 14. And lo and behold, that is where the universe is opaque to these things. So that's my guess as to why this is the case. And then there's probably some other background up here that you have to worry about. Don't know what that is that's creating this little bump. But this one is most likely the CMB. This one is definitely the cosmic infrared background. So it's opaque to photons. You can't detect photons of these energies. And as a consequence, you have to find some other particle to deliver that information to you. And the particle of choice is the only one that's available to you now is neutrinos. So if you have some energetic phenomena that exists in a distant blazar, you can only study it through the detection of neutrinos that come from them. So you look at the neutrino spectrum, what are the energies of the neutrinos, what directions do they come from, and that can give you information about distant galaxies, the high energy phenomena that's going on in distant galaxies, at distant star forming regions, and so forth. Let's see. Are neutrinos a form of radiation? Neutrinos, it depends on what you mean by radiation. So radiation is the exchange of usually a gauge boson, so that would be like a photon or a gluon, that would be radiation. Most people think of radiation as just the emission of photons, but another definition of radiation that is frequently used in cosmology is anything that is moving close to the speed of light. And so in that definition, if that's the sense that you're talking about, then neutrinos move very close to the speed of light, and so they are considered radiation in some contexts. But they're not radiation in that they're not made out of, it's not an electromagnetic field. So there are a variety of different definitions that are in use for the term radiation. They're not radiation in the form of light, like the way that we think of light, but they are radiation in the form of high energy particles that are moving close to the speed of light. So that's depends on what you mean by radiation and like what people in the discussion mean by radiation. Yeah, and we'll take a look at some of the results from this. All right, so that is the reason that you would build this IceCube detector for high energy stuff, because you want to look for what kind of physics is happening at large distances and at high energy. For short distances and low energy, we can just see that with infrared, the radio waves and X-rays and stuff. For high energy physical phenomena at large distances, like what's going on in the very early universe so you have to look at the most distant objects, neutrinos are the only option that we have. That's the only game in town. So you need to build a detector that's able to detect them. However, as I mentioned before, the highest energy neutrinos are rare. And so you have to have a large detector volume in order to see them. And that is where, so there you go. That's the design of IceCube. All right, so that is this one. Let's take a look and see what other graphs we have. So this kind of shows the astrophysical neutrino flux So it's the energy squared. It's kind of, they have these weird terms because they normalize because there's actually a really steep decline, and so they adjust it somehow. GeV per square centimeter per second per steradian. So there you go. GeV, that's energy per square centimeter, because astronomers use centimeters for who knows what reason we use centimeters. I hate the fact that we use centimeters, but some people really love it, and so we're stuck with it. Per square centimeter per second, and then this per steradian means what angles can they come in. So you have to integrate across the dome of the sky and across every square centimeter apparently to get this. And so this shows that you get the lower energy stuff, you get more lower energy stuff, and then it declines when you go to higher energy. This is the stuff from IceCube. So these are IceCube. These red points are from the Fermi telescope, the space telescope. And then these data points over here are from IceCube, combined in 2015. So this is really high energy stuff, right? This is TeV, and you're looking at 1,000 TeV. 1,000 TeV. That is super duper high energy. Okay, I mentioned already that the muon neutrinos will travel in a line. So here's an example of a muon neutrino. I believe that the color coding here, I guess we can look at it. I believe that the color coding here, it doesn't say, but in other animations that I've seen, the red is the early part and the green is the late part. So the red is the early part of the detectors firing, and then as time goes on, you pick up signals in the green and in the blue. All right, so in this case, you can see that you produced whatever the particle is that starts emitting the light. Over here, you can see how the detector strands are illuminated. Now, this is traveling at the speed of light, mind you, so this is just a few fractions of a second in order to get all of the light collected by all these detectors. And so they can see, oh, it arrived at these detectors at this time. As the Cherenkov cone kind of spreads out and starts hitting things, the Cherenkov cone meaning the Cherenkov cone of radiation that's produced by the decaying particles. Okay, so what was I talking about? Oh, and you can see that it's in a line, right? You can see that all of these things are moving in this direction, and so you can trace it backwards and get the direction that it came from. So that is a muon track that has this long line of detectors that fired. Okay, so there's your long line of detectors that fired, where if you had an electron, it would kind of spread out very quickly. Question is, do we have a limit on the minimum neutrino mass? We do have a limit on, well, the minimum neutrino mass is 0 for one of them, and we know from the neutrino oscillations what the other ones would have to be if the lowest mass neutrino is indeed massless. We have an upper limit on what the neutrino mass can be, and that's from the Catron experiment. And I have an earlier stream where I talked about the Catron experiment and how it is designed to put constraints on what is the maximum mass that the neutrinos can have. All right, so here's an example of them studying neutrinos that arrived in coincidence with the gravitational wave observatory, or gravitational wave observations. So gravitational wave thing, it has this, it's got to be in these different parts of the sky. That's based upon the arrival time of the gravitational wave in the different detectors around the world. There are 3 detectors in particular that are most important. That's the 2 LIGO detectors and the 1 Virgo detector. And so the detection of the gravitational waves in these different detectors localizes where these things can come from in space. And they also looked for, what neutrinos arrived that were coincident with this in-spiral. And it doesn't appear that these ones really had anything to do with those gravitational waves, but it's a way of placing constraints. So this is a demonstration of multi-messenger astronomy. Hopefully at some point we get gravitational wave signatures that produce neutrinos that you actually detect. Neutrinos don't interact with hardly anything, and so it's rare to get a neutrino at all. So we got to be happy with what we get. Here is a movie, High Energy Astrophysical Neutrinos. This movie shows basically how these things light up. So we'll take a look at it because that's what we're here for. So here's the particle coming in, it hits, and then that Cherenkov cone, the light spreads out, and there you go. That is the type of signature that you'll get in these detector strands. Gotta admit, that's pretty cool. So this was an actual one. That first one I think was a simulation. This one's an actual one. from 2011, 1.04 PeV. That's 1,000 TeV, which is 1,000 times the energy. Now, just to give everyone an idea of how big this energy are, that is 1,000 times the energy of the Large Hadron Collider. Well, 100 times the energy of the Large Hadron Collider. So the Tevatron at Fermilab was 2 TeV. It was a TeV in both directions. The Large Hadron Collider at CERN, it's like 7 TeV. I think that they've upgraded it so that they get like close to 10. Originally, it was designed to be up to 14 TeV. So anyways, it's like, we'll pretend it's 10 TeV. These are 100 times bigger than that, 100 times the energy in the collision. Now, this is actually important because there are a number of people who are concerned that, the Large Hadron Collider is going to create black holes and we're all going to die. There are higher energy collisions coming from space through these cosmic rays than what you can produce in the Large Hadron Collider. And so if you could produce black holes that would swallow the Earth because of high energy collisions, the Earth would already have been swallowed. So anyway, we can see this one, and that is the detectors lighting up. Note that these are traveling at the speed of light, and so these arrival times are nanoseconds later. You have something like 100 meters between them, and so 100 meters is 3,000 feet, so it's 300 nanoseconds, like just about half a microsecond later. All right, cosmic ray physics. So cosmic rays are typically come from a variety of sources. They could be stellar explosions, they could be magnetic recombination events, things like that. But they're basically two different varieties of cosmic rays. One is protons that are flying through space, and the other is like iron nuclei, because these are fairly common to make. But they could be other heavy nuclei, right? You could have oxygen or something like that. But basically they divide them into light and heavy. And all of these particles, they're all charged, right? They're stripped of their electrons and they're flying through space with an electric charge associated with them. And so cosmic rays are not, they're a dangerous detector if you're trying to study something. So if you see a cosmic ray, here's the Earth right there, and you're looking and you see a cosmic ray come in from this direction, that doesn't mean that that's where it was produced. Okay, it takes a real special kind of cosmic ray to be able to persist in the direction that it started from. It takes super duper high energy cosmic rays to do that. When I talk about the Pierre Auger Observatory, we'll get into some of those details. Generally speaking, though, the cosmic rays are, you have a stellar explosion over here, the particles leave, because they're charged, they get deflected by the magnetic field. The galaxy has its own magnetic field, so here's the artist's rendition of a magnetic field. And so the cosmic rays are going to kind of wander around like this through the magnetic field, and then it will come in, and then it will hit the Earth. And so you're looking back this way. You don't want to assume that it's coming from some other source over here, because it could be coming from a source clear on the other side of the galaxy and have followed this strange path in order to get to your detector. And as a consequence, it travels different distances. So if you have two cosmic rays that arrive at the same time, even if they're from the same direction, it doesn't necessarily mean that they came from the same source. There's all sorts of varieties of ways that cosmic rays evolve through space before arriving in your detector. Nevertheless, there are that really high energy stuff won't be deflected very much. And so if you can get super high energy cosmic rays, then the deflection is relatively minimal. And so you can use that to get some direction about where they may have come from. But for the most part, cosmic rays are coming from objects in the galaxy, wandering through the magnetic field of the galaxy, and then coming in towards the Earth. All right, let's see. Neutrino physics. So they're looking for the deep core subdetector. Allows IceCube to extend the measurements of neutrino flux from 100 TeV down to below 10 GeV. So 100 TeV down to 10 GeV is what? That's 4 orders of magnitude weaker. So it's like 0.01% of the energy. And for those ones, you need to have the detectors closer together, and that's what the deep core is. And so this one is looking for atmospheric oscillations and other things comparable to detections, or the detector capabilities of MINOS, that's a Fermilab experiment, TDK, that's a Japanese experiment, and Super Kamiokanda is also a Japanese experiment. They can look for sterile neutrinos, so this is constraints on sterile neutrinos. If there is a sterile neutrino, it's a neutrino that doesn't interact with matter because it's spinning the wrong direction. And that could be the dark matter. Anyways, this is a constraint on sterile neutrinos. They haven't been detected yet, but that's a constraint on them. Dark matter. You might be able to produce these kinds of things through dark matter or get dark matter annihilation, and then you use the IceCube as a detector volume for a dark matter detection. Let's see. I haven't actually seen this image, so let's take a look at it and see if we can decipher what it is that it's talking about. IceCube. So these are different constraints on the cross section. So sigma is the cross section for what? Neutrino to proton cross section. So here is the cross section in very small numbers, right? This is 10 to the minus 40 square centimeters. That's a tiny number. I think that's a barn because it's the broad side of a barn. Anyway, so this is a tiny cross section of the interaction cross section of hypothetical dark matter particles with the protons in your detector. So the hypothetical dark matter particle is this chi, and then the protons in the detector is this p. And what do we get? We have 3 different types of detectors and 3 different types of interactions that you could produce. So this is a tau plus, tau minus. So those are tau production. This is W plus, W minus, and this is bottom quark and anti-bottom quark production. You have 3 different detectors: Antares, which I don't know what that is, so that's something for another time. Super K, which we've talked about, that's the neutrino detector, and IceCube, which is the one that we're currently talking about. And then you see, so those are the 3 different detector types. You can see the cross section that they can eliminate, and then this scattering of points down here. The scattering of points down here are supersymmetry. So you have available parameter space in supersymmetric dark matter. Like if supersymmetry is real, then you have different dark matter particles that you can produce from it. They have different properties. It's hard to constrain those properties, and so you take a random sample of available properties, and you get this supersymmetry models that would predict dark matter particles with this cross section and this mass. Mass is on the horizontal axis, and then you make these measurements. And if for example, IceCube, so IceCube is the solid stuff. If the dark matter particles tend to decay into tau plus, tau minus pairs, then you can constrain these cross sections by this solid line. So this is the IceCube limits on dark matter particles that produce tau plus, tau minus pairs in their decay, or that preferentially would produce those. So notice that it excludes this big blob of stuff up here, which indicates that the dark matter is less likely to be of the form that produces this type of interaction, and more likely to be, if it has these masses, to be of the form that would produce this type of interaction, which has relatively weak constraints, right? It's a factor of 100 weaker, the constraints on this type of interaction compared to the constraints on this type of interaction. Anyway, so you can do dark matter detection with the IceCube detector as well. And they did this thing on glaciology, right? So you have all these detectors that are embedded down in the ice, and so as the ice moves over the course of a year or flexes, you can see that by looking at how the detectors move relative to each other. So that's kind of cool too. You have all these things embedded in the ice, and then you can watch them evolve. And apparently it says in this thing that there's bedrock underneath it, and the bedrock has features, right? You can bounce sound waves off of the bottom to detect features on the bottom. And so as the glaciers are moving, they conform somewhat to the ground underneath them, and that deformation translates into deforming the array of detectors in the IceCube. So that's something also that I thought was pretty cool. So there you go. That is what IceCube does. It measures high energy neutrinos. You can get, this one shows also reported measurements of all particle cosmic ray energy spectrum and energy range from 1.6 PeV, that's 100 times the energy of the Large Hadron Collider, to 1.3 EeV. 1.3 EeV is almost a million. It's 100,000 times the energy that you get in the Large Hadron Collider. That is really high energy. So there we go. Let me see if I can answer any questions now about IceCube. So that's IceCube. It's producing results now. Pretty interesting stuff. Do we have, let's see. Are all missing transverse momentum in particle accelerators neutrinos? So missing transverse momentum. So when you have a collision in a particle accelerator, so here is your beam coming in from both directions. You have your detector like this. I should have drawn it like that. So here's your detector. It's like a cylinder. The particles come in, they collide with each other, and then you get a bunch of jets that come off in the sideways directions because the momentum cancels in the head-on direction, and then all this stuff comes off on the side. And then the question is, if you were to look down the bore, so here is the bore of the detector, the beam is coming in like that, and you have a bunch of jets of material coming off here, and maybe some jets of material off here. If you have missing energy on this side, so like no jets, the question is, are these all neutrinos? And the answer to that question is, we don't know. Neutrinos are ones that we know about, so we know what neutrinos look like and how they interact. And so we could say, so some of this missing transverse momentum, transverse meaning perpendicular to the direction of the beam, so they could be neutrinos. They could also be dark matter. So if you were to produce, so this is also a signature of dark matter. If you produce a particle, it's a dark matter particle, and it comes off in some direction, it will carry momentum with it, but that momentum doesn't show up in the detectors, right? There's no way to track that momentum because dark matter particles don't interact very much. And so you would have missing momentum in the transverse direction. You'd see particles coming off here, carrying momentum in this direction. Because momentum is conserved, there must be some other particle going off in this other direction. And if you don't see it, your options are neutrinos or dark matter. If they were neutrinos, I suspect what you would get is, because neutrinos come from leptons. Neutrinos come from the decay of muons and taus. And so if you have muon and tau tracks that are coming off here, and you can get that, you can tell that it's a muon or a tau because let's say that you produce a muon. Here it is, you produce a muon that's coming off in this direction. It will curve, because there's a magnetic field threading through this, it will curve with some size. You'll measure its arrival time so you can measure how fast it's moving in this direction and what its radius of curvature is. And you can transform that, you use the Lorentz force law basically, to get the mass. So you can measure the mass of this particle. And once you measure the mass, then there's only a handful of particles that it could be. So if it's a muon, it will have the muon mass. And then you can say, okay, there's going to be some missing momentum going off in this direction, and because this is a muon, that implies that you might get a muon neutrino going in that direction that you don't detect. If it curls more tightly, then that would be an electron. If it curls more slowly, then that would be a tau. If you have a proton, proton has a mass that's different than all of these things, so it's going to have its own curved path. If this is an electron, it's going to curl this way, and the proton would curl the opposite direction. So you can tell the direction that it curls and the radius of curvature of the curl and the arrival time of the signal in your layers. You have layers and layers and layers of detectors in here to track so you can track how fast that particle is moving. What energy did it have to start with? Okay, let's see. What other questions do we have? Can there be detector inaccuracies or algorithmic ones? Detector inaccuracies, those they can calibrate, right? They can put in specific types of particles and see and calibrate their detector so that they can determine what fraction of stuff they miss, and then they just need to get a signal that's bigger than whatever their bias happens to be. The CMB image, we see, how do we know how accurate the map is if you say the direction of origin can't be trusted? With the cosmic microwave background radiation, that is different, right? The cosmic microwave background radiation, these are long wavelength photons. If we go back to this image, cosmic microwave background radiation, that's low energy photons, right? Micro EV. The universe is transparent to CMB photons. And so when we see a CMB photon coming from a particular direction, we know that it came from that direction, with small exceptions. And that small exceptions is the fact that there is going to be intervening matter. So you're going to have, like, here's us. So now we're talking about the CMB. You might have clumps of dark matter or something like that, or galaxy clusters. And so you have a CMB photon coming from back here. So here's the CMB, cosmic microwave background. This photon arrived here, and it may get deflected slightly by these different things. And so we don't get exactly a straight path. But you can actually measure the effects of intervening mass on the spectrum of cosmic microwave background photons. But in general, the CMB photons come directly from the CMB in a straight line to us. Where what you run into with the high energy cosmic rays, and in this case also the high energy gamma rays, is that you'll get a high energy gamma ray, which there are fewer of them, with one CMB photon, and then you pair produce. And so you lose some energy, you lose some small amount of information about the CMB, but the number of CMB photons is way, way bigger than the number of TeV photons. So it's, you lose information about the TeV source, but the amount of information, so you lose all of the information about the TeV source, and you lose very, very little information about the CMB source, the direction of the cosmic microwave background. So it just kind of like plucks off one thing at a time. All right, will IceCube detect next Friday? Next Friday the movie? That I don't know. That'd be pretty cool if you had both IceCube and IceCube in the same movie. So like he sets up a barbershop, for example, on the South Pole. Can't bend high energy neutrinos to find his math. So you can't bend high energy neutrinos because they don't couple to anything other than the W and the Z. And so you can't put them in a magnetic field in order to, there's no charge that they can couple to the magnetic field and as a consequence curve. All right. Any other questions on IceCube? If not, then here's the plan. Number one plan, not this week, not next week, not the week after, but in July, I'm going to start a new thing. So we're going to continue doing experiments, but I'm going to add to it this idea of going through the AP Physics class and talking about like what's really going on in AP Physics. So AP Physics is kind of a hybrid between college level physics and high school level physics. And we're going to go through and get the fundamental stuff in each of the lessons. So we're not going to do like, here's what the formula is, here's how you calculate stuff. We're going to talk about like, what's the deep underlying physics there's no time to cover in a class, and we'll cover it here because I think it'll be an interesting walkthrough of all of physics with some way of organizing it in an order. So I've started working my way through that to kind of list out the things that I want to cover. I should be far enough ahead that beginning in July, I'll be able to do that. There are a couple weeks where I'll be gone simply because that's the nature of the summertime. But I'll start that in July. I will keep doing these physics experiments because I still have a long list of things that I want to cover in the physics experiments, so that should be pretty cool. Let's see. Do you tell my students to watch my stream? I don't usually tell my students to watch my stream. I mean, I tell them that it's available if they want to, but it doesn't have to be. What is the W and the Z, and what do they couple to? So the W and the Z are the equivalent of the photon. So the photon is the particle that is exchanged in the electromagnetic force. So when there's an electromagnetic interaction, it happens through the exchange of photons. When something happens with the weak nuclear force, so it's a different force, it's also through the exchange of particles, and the particles that are emitted there, or that are exchanged there, are the W and the Z particle. So the W and Z, they are massive, they have mass, unlike the photon, which is massless, but they are effectively the same. You can think of them as the radiation that you get for weak nuclear interactions instead of electromagnetic interactions. So the W and the Z, it's a weak nuclear force, and that means that they couple only to quarks and leptons. And when it comes to leptons, it's the only other force really that they couple to. They couple to gravity, the charged leptons, so that would be the electron and positron and so forth. Those can couple to the electromagnetic force, but neutrinos only couple to gravity and the W and the Z. So gravity and the weak force.